All right. Welcome back to another episode of Science with Surback. Today we're going to continue on with our equilibrium unit. And in this section, we're first going to review a little bit from what we did on day one notes. And in day two, we are going to expand a little bit upon what we went over in our day number one set of notes. Okay, so the first thing that I want to identify or want to review is this. Remember, in equilibrium, very important concept is that in the equilibrium expression, we are only utilizing states of matter or substances with states of matter that are either AQ for aqueous or G for gas. There is absolutely no solids or liquids in our equilibrium expression. Now, K, and remember it's big K. Big K here is unitless, all right? K can tell us a lot there, all right? And then the third thing I should mention before we move on to magnitude is that equilibrium expression, products over reactants, products over reactants, products over reactants. Really important that we understand that. Now, magnitude, basically that means, hey, in terms of K, what's that mean? So if K is bigger than 1, the products are going to dominate, meaning at equilibrium, there are more products present than reactants. If K is less than 1, we say that reactants dominate. And so at equilibrium, there are more reactants present than products. Okay. A large K, again, more products. Small K, more reactants. Right. Now, our final thing that I'll say here is that if K is bigger than 1, we say the equilibrium lies to the right or with our products. And if K is less than 1, we say equilibrium lies to the left or with those particular reactants. All right. So let's go into a little bit more detail here. And let's talk about some other aspects of equilibrium. Okay. So from yesterday's set of notes or from day one set of notes, we looked at this and we said, okay, we can find the equilibrium constant, big K, for our equation here. And if you remember, we had a couple of different things that happened, okay? Number one is in general our expression, okay? And that is big giant K equals products over reactants. Now, our only product here is NO2. And here's our thing to remember. That 2 is going to be our power. Okay? So in an equilibrium constant expression, that 2 is our power. So I have NO2 to the second power all over our reactant, which in this case is N2O4, and that's raised to that coefficient of 1, which we'd list as that, right? So that would be our equilibrium expression. And then all we would have to do to solve this problem is plug these specific values back into our equilibrium expression. So I'm going to change colors here, and I'm going to say, let's actually solve for K here, given our equilibrium concentrations. So NO2, remember NO2 is on top here. And if we put this in, I'm going to put it in green color here, NO2 is on top. So at equilibrium, we have a value of 0.0310 molar, okay? Now you don't have to put the M, but I just do because the brackets represent that as well. Now we can't forget the expression said, hey, square that, okay? Now what we want to do is this. We want to divide it by our particular reactant, our substance N2O4. And so on bottom, we are going to put in brackets there 0.00452, and we go through this, okay? So we have products over reactants, okay? And I guess technically, since I did it up top there, you don't have to put M because the brackets represent M. I'll just do it to be consistent here, okay? So what we need to do is this. We need to take 0.0310, we need to square it, and I get 0.00961. I divide that by what's on bottom, 0.00452. I press enter, and my equilibrium expression there, or my constant, our K there, is 0.213. And we got that answer from yesterday, okay? So now, and remember, K is unitless and would look like that, okay? So that's what we got from yesterday, a little bit of a review from our math problem. And so now what we can do is this. Well, we now want to double our coefficients, okay? So let me write down what the actual equation would look like if we double our coefficients, okay? And so what we need to do is this. We need to think about, first off, what happens to our equation. And this is exactly what would happen. We would have 2 into O4 as a gas. And remember our equilibrium lines there. And then we would have 4 in O2 as a gas. And we would put it back in our expression and say, okay, well, let's say we're still at equilibrium and we have these concentrations up here. Well, what happens here is numerically, our equilibrium expression would now become K equals the concentration of NO2 now to the power of 4, all divided by our products, or excuse me, our reactants on bottom into O4 now to the second power, okay? And so if we plugged our numbers back in, we said, all right, K, we're still going to use NO2 as 0.0310. This time we're going to raise it to the fourth power, all divided by our 0.00452 raised now to the second power. Let's see what happens here in terms of our number. So I'm going to take 0.0310, I'm going to raise it to the fourth power, and then I'm going to divide that by 0.00452, and I'm going to raise that to the second power. And what I get, my K in this situation here, is 0.0452. Now, that was a lot of work just to do that, okay? And so what we can do is a little bit of a shortcut, okay? And so what we can do is this. If we double or we manipulate our coefficient, we can do the same exact thing, get to the same exact K value here by taking the power to whatever we manipulated the equation to. So let me show you what I mean by this. We doubled our coefficients, which means we increased by a factor of 2 there. And so if we take our original K here, which is 0.13, and we have 0.213, and since we doubled our equilibrium constant, we're going to say root 2. Okay, so we take 0.213 root 2. I get 0.0454. Now, because of rounding and things of that nature here, that is close enough here. And if actually we would keep that in our calculator from our first equation, we would actually get 0.0452. okay? And so I'm going to say, hey, pretty much this equals the same thing that we have down there at 0.0452. All because we doubled our coefficient. We took the original k to that particular power, okay? Now, if we reverse the equation, so all I'm going to do is take our original equation and I'm going to flip-flop things down here. I'm going to write this in blue, okay? So now we're just flip-flopping, and so now we have 2 NO2, and we got our equilibrium expression, and then we have N2O4, and I should have inserted states of matter here. We have gas and gas. So we have gas and our gas. Okay, and so we have our original equation that's now just flipped. Well, now by doing that, we have a K that is equal to, now, since N2O4 is a product, N2O4 raised to the first power, all divided by NO2 raised to that second power. And so we'll just plug our numbers in from up top there. Okay, so now we get K is going to be equal to N2O4 is still 0.00452. And that is raised to the first power, all divided by 0.0310. Okay, that is raised to the second power. So let me plug this into my calculator. Okay, so I'm going to get 0.00452 divided by 0.0310, and that value down on the bottom is squared. I get a value, I get a K of 4.70. Now, again, that was quite a lot of work here. So why don't I see if I can take my original K, which again was 0.213, and see if I can do something here with this original K value to be able to express it in something useful, okay? And so here we go, all right? If we reverse our equation, we can get that same K value by taking 1 over the original K value, or what we would recall that as our inverse. So 1 over 0.213. I'm going to punch it in my calculator, see what I get. 1 over 0.213. And I get a value. I get 4.6948. By the time we round, that would be a K value of also 4.70. So my point with this slide is that we don't have to completely switch around the equation and essentially waste our time. We have some rules, if we change around the equation, that we can abide by. Okay, so let me go to the next slide here and let me show you our specific rules. So number 1, if you reverse the direction, the K is 1 over that original K value, or what we were called that as the inverse of our K value. Okay. Now, if we manipulate, we multiply and or divide, we take our original K and we raise it to that particular power. Our last thing I didn't show you, which I will on an example here, is that if we have a series of steps added together, our K values, all we have to do is multiply them. Okay, so we wouldn't have to find individual K values and go through that. Or if we did have multiple steps, we could put them all together. So let's try this out in a couple examples here. Okay, so our example, it says, hey, you are given these top 2 things. You want to find out what is the K value for this bottom reaction. Okay, so this is a lot like Hess's law, which is covered in thermochemistry. But I want to show you how we can take our top 2 equations with known K values, and we can get to our equation down here and find that K value. So the first thing that I'm going to do is this. I'm going to look at what I am given, okay? And so what I am given on the left-hand side is HF. Specifically down here in this equation that I'm interested in is 2 HFs. And so I look at the equation up top here, and I can see that equation number 1 gives me 2 HFs. Or excuse me, how about just HF? It does not give me 2. So what I need to do is I need to multiply this particular equation by 2. However, since I multiply this equation by 2, I'm going to have to manipulate my k, okay? And so let me write this down, okay? So I have 2HF, which is an aqueous solution here, and we draw our equilibrium arrows. And then I have 2H pluses, still aqueous, and 2F minus, also still aqueous. And again, instead of rewriting my equilibrium expression, all I have to do is, because I multiplied everything by k, I just have to take this number and root it to that particular power. So all I have to do here is, in parentheses, I'm going to take 6.8 times 10 to the negative 4th, and I'm going to square that because I doubled the coefficients. And now my k value for this equation down here, I'm going to write in purple, is 4.62, or excuse me, 4.6 because of 2 sig figs, 4.6 times 10 to the negative 7. Now, Hess's law also states, hey, once we use it and manipulate it, go ahead and cross it out. Okay, great. Now, the next thing I need is this. If I look down here on my bottom equation, I see that I need C2O4. So C2O4, if I look up top, is on the right-hand side. It's on the wrong side. So what I need to do is I need to flip-flop these equations, okay? So I'm going to flip-flop the equations here, and I am going to do this. I'm going to have my 2H pluses, which are aqueous, and my C2O4, 2 minus, which is aqueous, goes to equilibrium here, or we draw those equilibrium values here of H2, C2O4, okay? And because I flip-flop my equation, my k is going to change. So to find my new value of k, what I'm going to do here is I'm going to take my original value of k, I'm going to take the inverse. So I'm going to say kc is equal now to 1 over 3.8 times 10 to the negative 6. Okay, so I'm going to take 1 divided by, parenthesis, 3.8 times 10 to the negative 6. And when I press enter here, I get a value. Here of 2.63, which is going to round to just 2.6, times 10 to the 5th. So my value here of our k is 2.6 times 10 to the 5th. Okay? Now, what I want to do here is this. I'm going to add together my blue and my purple and my green equations here. Okay? So I'm going to add together this stuff. And oh, by the way, I should probably cross that out because I already used it. I'm going to add these two equations together. But remember, when we add equations together, the same substance on opposite sides of different equations gets canceled out. So this is going to cancel out my 2H pluses on each side. I double check, nothing else can cancel. And so all I'm going to do is add my purple and my green equation together. And I'm going to say, okay, I have 2HF. Okay. Then my only other substance there on the reactant side is C2O4, 2 minus there. Okay. Nothing else is on the left-hand side of either the purple or the green equation. And so I draw my equilibrium arrows, and my items on the right-hand side are 2F minus plus my H2C2O4. Now, this is our check, right? We added the equation together to get what we want. So all this blue one does, it serves as a check. That equation we want, right above it, written in black, matches up. So check. That means all we have to do to find our K value is take our manipulated Ks from the equations that were given here, and I box those in blue. And so to find our Kc value of our equation here, we just take this. We would say, hey, take 4.6 times 10 to the negative 7th times 2.6 times 10 to the 5th, and that will get our K value of what we want. So I'm going to write my Kc actually up here. And so in my calculator, I'm going to take 4.6 times 10 to the negative 7th times 2.6 times 10 to the 5th. And I get a value here. I get a value of 1.2 times 10 to the negative 1st. So a value of 1.2 times 10 to the negative 1st. Okay, so right here, this whole thing would be my K value of that equation I've just taken into account. So the point of this was to show you, hey, we can manipulate our particular K value into items that we want by abiding by these certain rules that dictate or determine what happens to our equilibrium expression and our equilibrium constant.